For people, well, people who took or were here in Tuesday's lecture, I'll say it again on the final. When you take the final, I don't want to see you ever again until I turn in grades. That said, there are still, time is short, and I have to use it efficiently. If you have problems with the test and how it was graded, if you think something should have been corrected, or if it was just an arithmetic error, take photos of the missing homeworks, if it's got a score on it, put your student ID on it, and then send me the photos with a brief explanation about why you think it should be corrected. I won't deal with it before the final, but I will deal with it after the final. Because after the final, I've got, oh my goodness, I've got 3, 4, 5, 6 whole days to worry about getting grades done. So if you still have problems, if you're missing, now granted, you know what I'm talking about. You can sit there and promise me all day long that you've looked everywhere. Keep looking deeper. Look into that homework bin, and you will find it eventually. It's one of the reasons why I curve the homework heavily, because I assume everyone has lost 1 or 2 homeworks. Period. So it will get fixed through that way. Now, if you honestly have a homework that's graded and it shows up at a 0 on Blackboard, email me a photo and I'll deal with it. After tomorrow's tutorial, which is at 1 o'clock here, after that tutorial, I'm going to be in finals writing mode. And on Monday, I may have some time, but that time will only happen after I've printed the final. Until I've printed the final, I'm not going to want to talk to you. It has to be done. There is no postponement of the final. Any questions? What we're going to do today, now if you suddenly have a desire to talk about something else, like a finals question or something, let me know and we can handle it. What we're going to do are the problems of the test. This is test 1. I'm not sure what version. Probably it was the conversion number 31. And we'll just go through this. First. In fact, what I'm going to do, all right. There probably will not be a conversion problem on the test. The conversions will occur within the problems. And I'm just going to skip it. For the vector addition, you will have a vector addition problem similar to this. Three meters at 270. 4 meters at 135. One of the vectors, in order to save time, will be an instant conversion vector. That's A. 270 degrees is the negative y-axis, so this is negative 3y hat. The 4 meters at 135, if that's 135, then the reference angle is 45. By is b sine theta. Bx is b cosine theta. These are the reference angles. So 4 sine 45 is 2, and 4 cosine 45 is something else. 2.83. It's a second quadrant vector, so this becomes negative x and positive y, negative 2.83 x hat plus 2 y hat. So the resultant in component is negative 2.83 x hat minus y hat. And that's meters. And so that is a vector addition really quick. The polar version, which you'll have to do as well, negative 2, 1, that's the reference angle. This is the absolute, which will be 180 plus theta r. Cx is 2.83, Cy is 1, so C is 2.83 squared plus 1 squared, square root. Ooh, and that actually turns out well. So this is 3 meters. Now, reference angle, inverse tan of y over x, which is 1 over 2.83. The way that I do this reference angle system of vector addition is that we do not let the signs tell us what to do, we tell the signs what to do. Inverse tan of 2.83 inverted is equal to 19.5 degrees. So theta absolute is 180 plus 19.5, or 199.5 degrees. So the resultant in polar notation, C is 3 meters at 199.5 degrees. And so that's a vector addition. You will have to do this on the final. Number 2, 2D motion. I promise you, knowing how to do a quadratic solution or quadratic formula will not be expected on the final. Here, you are given the time. I'm looking for the final point of contact. The cliff height is 50 meters. The angle is 30 degrees. I want to know what V0 is, and I want to know what X is. When doing a two-dimensional motion problem, you pick the origin. I tend to pick it at the lower left corner here. Then you write, we do the typical X or up and right is positive, the others are negative. X equals X0 plus V0 XT, and Y equals Y0 plus V0 YT plus 1/2 AT squared. A in this case will be -10. You identify your zeros. X0 is 0, Y final is 0. We're looking for X, we're looking for V0. Because this is a two-dimensional motion problem, V0 Y, V0 X. V0 X is V0 cosine theta. V0 Y is V0 sine theta. And I get this. I'm looking for V naught and X. So this is a 2 equation, 2 unknown problem. So we're going to solve for one variable and plug it in the other. V naught is X over T cosine theta. So 0 equals Y naught plus X over T cosine theta sine theta T plus 1/2 AT squared. T's cancel, that becomes a tan, and I'm looking at 0 Y naught X tan theta plus 1/2 AT squared. I know everything except for X, solve for X. Minus Y naught minus 1/2 AT squared equals X tan theta. So minus Y naught I get that. Oh, no, I don't want that. I want this. So I'm left with minus 50 plus 1/2 negative 10 8 squared tangent of 30 degrees. And that will be my X. And I get 467.7 meters. Solve for V naught. V naught X T cosine theta 467.7 divided by 8 cosine 30. $67.5. And that's a 2-dimensional motion problem. Typically this will be the 2 equation 2 unknown.
Why is the sine over cosine?
Sine over cosine becomes tangent. That sine T is there. V naught is X over T cosine theta. I forgot to put the sine in, and then I realized it, so I scrunched it. Atwood's machine, motion. I give the masses, it's a very straightforward, I'm looking for time and I'm looking for acceleration. There is friction, boo friction. You've got the upper mass, tension, normal force, force of gravity, force of friction. On the other one, you have tension and mass, gravity down. Well, which is really M1. You do 2 of these equations. Now we're using the loopy-droopy number line. Up and to the left is negative, down and to the right is positive. We'll work on one first. Sum of the forces vertically is equal to 0, which is equal to normal force minus mg. So the normal force is equal to mg. So the friction force is mu sub k mg. There are 2 horizontal forces, tension and friction force. Sum of the forces in X is tension minus friction force, and that is equal to M1A. So M1A is equal to tension minus mu sub K M1G. Next, sum the forces on M2. Sum the forces vertically. That is M2A. Tension is up and to the left, negative. M2G is down or positive. So tension is equal to M2A plus M2G. The whole goal is to find A. So I've got T is equaling to this and T is equaling to that. Set them equal to each other. M2A plus M2G equal M1A mu sub K M1G. A's on one side. Non-A's on the other. A G A is G and I get this. Let's see if I did everything right. Looks legit. I'm having a problem with can't see it because the number, this is a small number, I'm subtracting from it a big number. Now I'm flummoxed. That over. A would be negative in this case, and that's not what I want. I'm looking at the numbers. Friction force mu sub K Fn minus friction force M1A. M1A is T minus mu sub K. That comes over M1 plus that. That looks legit. M2A is M2G minus tension. Ah, where did I go wrong? Going from here to here, I made the mistake. That jumps over here. That jumps over there. That goes from negative to positive. That goes from positive to negative. So if that becomes negative, then that's negative. That comes there and makes this negative, which makes this negative M1 or M2 plus M1, which makes this negative of that. Okay, so that's fixed it. When you look at this, and this is one of the things that you learn as a physicist, I'm staring at this equation and I'm going, my A is negative. This is the system that's definitely higher than this. The forces are all causing this to go right and down. A should be negative, or A should be positive, excuse me. So when I saw A being negative, part of my brain started screaming, and now I can get the right answer. So let's get that. When you're doing these Atwood's machine problems, it's acting only under the influence of gravity. If this is the case, the acceleration should only be positive and less than 10. If this number ended up being negative, which we almost did, I would definitely go back and double check everything. Also, it can't be greater than 10. You can't have an Atwood's machine without rockets or external forces to cause this thing to accelerate faster than 10. It has to be less than 10 and greater than 0. Yes?
How does the negative not go equal? Can we move it over to here? Like, how does it go?
When I go from here to here?
No, yeah, well, yeah.
So what?
How does it go to the numerator so the denominator?
Well, it doesn't. Negative.
Doesn't matter.
It doesn't matter. What's the difference between -1, 1 over -1, and -1 over 1? Nothing. It's the same thing.
So you would have the same answer.
You would have gotten the same answer. The negative sign in the numerator and denominator doesn't really matter. Yes?
So, I'm always going to add up the machine is supposed to be some force in Y and X.
Well, I'm summing the forces in Y because in this upper one, you need to know what the friction force is, and then I sum the forces horizontally, X. Here, the only motion is in the Y, the only forces are in Y, and so I stick to Y. Here I go X and Y, here I go Y. Now, the last part of this problem is a one-dimensional motion problem. It's M2 starts there and falls 20 meters. Solve for T. 2x over A is equal to T squared. So T. .4 seconds. And so that is, those are the answers we're looking for. All right. As to what version it is, I'd probably say it's version 31, whatever, or it could be the time. So it's either 31 or 8 for that version. All right, test 2. There will not specifically be a right-hand rule problem on the final. However, you'll need to know it like for torque bar and stuff. The first problem is the Fish of Fury. I have a stick welded onto the disc. The velocity of the fish is 10 meters per second and constant. I'm looking for alpha, angular momentum, and frequency. Well, alpha is 0. And why is that? dV dt is 0. V is equal to omega r. You can rewrite this as dV dt is equal to d omega dt r. This becomes alpha. dV dt is this. That's 0. R is definitely non-zero. Therefore, alpha must be 0. Basically, if that fish doesn't speed up or slow down, that spool will rotate at a constant rate. I'm looking for angular momentum. It's a disc. Oh, actually, I need to know. Oh, I definitely need to know what V is. V is equal to omega R. 2 pi F is equal to omega. So V is 2 pi F R. So the frequency is V over 2 pi R. V 10 2 pi 0.1. So it's 150, it's 50 divided by pi, whatever that is. .9 hertz. Also, angular momentum, the first thing we got to do is know what it is. That's I total times omega. Or we could rewrite this as I total 2 pi F. I total is the moment of inertia of the disk plus the moment of inertia of the bar. The disk is 1/2 mr squared and the bar is 1/12 ml squared. R is 0.1, L is 0.2. The stick is welded directly across the center of the disc from end to end. And so this will give you the moment of inertia of the system. So that's the angular, or that's the moment of inertia. The angular momentum 0.02 2 times pi times 15.9. Or 2 kilograms meter squared second. And I am a huge fan of knowing your units. Sit there and understand moment of inertia, kilogram meters squared. Angular momentum, kilograms meters squared over second. Angular acceleration, radians per second per second. All that stuff. For number 2, Atwood's machine with energy. You're either going to get an energy Atwood's or a motion Atwood's. This is an energy one. I want to know, given this final velocity, I need to know the second mass, and I need to know the fraction of energy remaining. So the initial energy minus the energy removed through friction is the final energy. The initial energy is the potential energy, M2GL. Now, work is friction force times distance, L. Friction force, you can go through the same derivation. The friction force is just mu sub K mg1, or actually m1g, and then L. The normal force is m1g, friction force, mu sub k m1g, using the derivation that we did before. The work is force times distance, so we get this. So it's mu sub k m1gl. The energy final is the kinetic energy of the two particles that are moving as one. Now I've written them out like this so that it's easier to separate them. They're already separated. I'm looking for M2, so it's M2GL minus 1/2 M2V squared equals 1/2 M1V squared plus mu sub k M1GL. You could do all sorts of things now. I'm going to factor out the M2. Oop. So M2 is this. M1 is 3. V is 10. Mu sub k is 1. So M sub 2 is 5. Exact kilograms. Now the fraction of the energy remaining is the energy final divided by energy initial. Energy final is just the kinetic energy of the two moving particles. The initial energy is just the potential energy of M2. And so this becomes 1/2. M1 plus M2 is 8. M2 is 5. L is 20. So 0.032 is the fraction of the energy remaining. Oh yes, thank you. I was wondering why that number was so low. So it's not M1 plus M2, it's M1 plus M2 quantity V squared. That was weird, okay. So the number is a lot higher than that. I'm sitting there going, well, it's not less than 0. I guess it could be right, but it's not. And now we're going to get a more legitimate number. 0.4.
What is
1/2 times the collective mass, 3 plus 5, times velocity squared, divided by the hanging mass, gravity, and distance fall. The last problem of test 2, the jump jet problem, or Harrier problem, you have one mass pulling down. You have two forces pulling up. What are the forces that we're dealing with? What I would do, you can pick any point to be your rotation point. I'm going to pick where F1 is, so that I don't have to worry about this. So if F1 is here and F2 is here, I've got mg pulling down. I picked that as the rotation point where R1 and R2 are there. This is not rotating, so sum of the torques is equal to 0. That means mgr1 and F2 R1 plus R2 are my two torques. mg is to the right and down into the page or negative. This force is to the right up positive, and then we got that. So mgr1 is equal to this. And I got this. M is 10,000, G is 10, R1 is 3, 3 and 9. So F2 is 25,000 newtons. You also know that the ship is not, or the plane is not going up or down. Sum of the forces vertically is equal to 0, which means F2 plus F1 minus mg is equal to 0. mg minus F2 is equal to F1. 10,000 times 10 minus 25,000 is equal to 75,000 newtons. Done. So it was just testing your knowledge of torques, expanding your horizons to understand that you don't have to have a fulcrum to have a torque bar problem. And that's the end of test 2. Test 3, what we just had, you're building pendula with zombies. Oh, and just as a side note for this, before I really get into test 3, I want to talk about something. Yes, either this or this. Those first two, torque or vector addition, definitely. 2D motion, definitely. Maybe, definitely not those specific problems, but something related. This or Atwood's energy or Atwood's motion will be on the final. This won't. It's a circular where alpha is 0. The one on the final will be where alpha isn't equal to 0. The other thing that Dr. Eschenberg really enjoys, doesn't really enjoy talking about himself in the third person, but he likes welding things onto each other so that you have to figure out the sums of the moments of inertia. So be able to add stuff up. I think there may be a parallel axis theorem part to it, where there's, rather than a circle with a stick across, there may be a stick welded onto the center and hanging off the end. Now, why would one need a circle like that? I don't know. But know the parallel axis theorem. We'll probably talk about that tomorrow in the review session, or at the end of this lecture. We still have a little over half an hour. It'll either be something like this or something like this. This is done with energy, that's done with motion. I have done on finals Atwood's machine problems where I give you the choice. You can pick either one. If I say find velocity, that's me telling you do energy. If I say find acceleration or the time that it takes to hit the bottom, you work with motion. So it's kind of within the problem itself what I recommend to do. This one gave everybody fits, so most likely there will be a torque bar problem on the final. So most likely not this, but something similar to it. Now for this, there could be some pendula problems. There's going to be not a Bernoulli's principle problem. There will be a buoyancy problem. There won't be an Atwood string problem. We're still going to do it because it has some things that we need to talk about. Doppler shifting, not sure. I mean, everybody knows about, I mean, it's getting tired of the roulette wheel problem or problems like it. But there will be stuff involving sound. Probably pluck a string or blow on a pipe, something like that. Stuff like that. We'll start, once I get done with this, we'll start answering other questions. For the Walking Dead test, simple pendula with an 8-second period, simple pendula is 2 pi L over G. We're on Earth, though I didn't say it, but it's just understood. The only thing that I don't know is L, so I'm going to solve for L. T squared, 4 pi squared, L over G. L is period squared G over 4 pi squared. So 8 squared times 10 divided by 4 pi squared. So 640 divided by 4 times pi squared. 16.21 meters. So you take the zombie, you attach it to the end of a 16.2 meter long string, and it will have an 8-second period. Spring pendulum with a frequency of 14 hertz. You get this. I gave you the frequency, so you rewrite period like this. And then I know what the zombie's mass is. The only missing value is K. So 1 over F squared, 4 pi squared, M over K. So K is 4 pi squared F squared M. And you get a really big number. 3.86 times 10 to the 5th newtons per meter. Problem 1, Bernoulli's equation, a fluids problem. On one of the versions, the pressure was negative, and I said during the test that it is a possibility. 2 of the 3 worked out fine. To do this problem, you need equation of continuity, solve for V2, so pi R1 squared V1 over pi R2 squared. Both of these, you can keep them in centimeters, because centimeters squared over centimeters squared doesn't matter. The units will cancel. There's no point to do the conversion. And the velocity is 8 meters per second. I think this is the guy that is negative. Bernoulli's equation, my least favorite equation. The density is 1,000, so, no, not that, kilograms per cubic meter. You look at the height, I set the base as height equals 0, so H2 will be 0. That means that P1 plus rho g h1 plus 1/2 rho v1 squared minus 1/2 rho v2 squared is equal to P2. Now I want the pressure in atmospheres, so you're going to take those 3 terms and divide it by 1.013 times 10 to the 5th. That means we have 1 plus, there's a row in each of these terms that I'm going to just factor out. 1,000, 10, 20, plus 1/2, 2 squared, minus 1/2, 8 squared, all divided by 1.013 times 10 to the 5th. Or this may not be, I'm not sure. 200 plus 2 minus 32. Oh no, this is going to be positive. Times 1,000 divided by 1.013 x to the 5th. So the answer that I get is 2.68 atmospheres. In one of the versions, this is so big that it overwhelms the whole thing. But 2.68 atmospheres. The last part is to calculate the total volume of the of water. Volume is A1 V1 times time. The flow rate units are cubic meters per second. Multiply it by time, you get cubic meters. So that's how you get the volume. A1 is pi R1 squared. So pi, now in this case we will convert 0.12 squared. V1 is 2, time is 20. And I have 1.81 cubic meters. And that is problem 1. Now for problem 2, the Atwood string, you know that the frequency of a string is NV over 2L, where capital L is the vibrating length. Velocity is the square root of tension over linear mass density lambda. V is now hanging mass times gravity over mass of the string L1 plus L2. Now how I got this is I know lambda is mass of the string divided by the total length, L1 plus L2. The tension is provided by the fact that you've got a hanging mass. Tension is the hanging mass, so MHG, 1 over lambda is L1 plus M2 over MS. So this becomes N over 2 L1 square root mass hanging gravity L1 plus L2 over the mass of the string. Now what was given in the test is that the frequency of the string is 1200 hertz. That is necessary to know. How does one get the hanging basket? The mass of the basket is nothing. The total hanging mass is thus the number of brains times the mass of one brain. So this comes this. Now I told you that the mass of the brain is 1,000 times the mass of the string. Substitute that in for this. One of the things that you have to do is understand that the problems that I'm going to give to you will have, on one occasion, a substitution problem. We're going to have to substitute out something that you don't know. Of course I didn't give you the mass of the string, but I did give you a ratio of the string to the brain mass. The masses of the string cancel. The goal is, I gotta find n. What is n as in number of brains? Square root, or square it. There's nothing in the denominator anymore. And then solve for n. And then you get this. So it's 4 L1 3 F 1200 Now, the one thing that we haven't figured out is the value of N. This is in a second harmonic. There are 2 antinodes and 3 nodes. So N is 2. L1 plus L2 is 9. And you know how I love to cancel stuff out. So I don't have to do that much work on solving for it. And I get 144 as the number of brains. I think the two version 6 and 8 were 144. Version 2 I think was 32. I think that was it. I will try to get solution sets of all the different tests and their versions up. One of the many things I got to do over the weekend. The last thing is a sound problem with Doppler shifting. You hear 1600 as it's coming at you and 1310 as it's going away. So this is towards this is away. You set it up like this because you have those two frequencies, but you don't have the source frequency. Cross multiply. Distribute. Get all your terms on one side, non-terms on the other. Factor. Solve for V. Sound is 350, towards is 1600, away is 1310. And I get .9 meters per second. Now the last part is determining the frequency of the sound emitted by the motorcycle. You can use either towards or away, it doesn't matter. Let's use towards. F over 1 minus V over Vs. F towards 1 minus V over Vs is frequency. So this is 1600, 1 minus 34.9 over 350. and I get 1441 hertz. And so that is the motorcycle problem, and all 3 tests done in an hour. So that was my plan for today. What would you else like to talk about? What? Huh? Energy or motion, correct. There won't be an outward stream. No. Outwards, to say that there is, I call it an outwards machine for test 3, that we just did. It's not a real outward. It's just the same. It looks similar. In the final, there will be a straight up outwards machine test 1, test 2 type of thing. So it's not anything like a bucket of rain. Yeah. Yeah, if you want to talk about anything. Did I do what? Yeah, let's do that. So this disc has 3 masses welded to the edge. The mass of the disc is 100 kilograms. The mass of each point is unknown, and that's what we're looking for. From rest, a force of 400 newtons accelerates this disc, causing it to rotate 100 times in 300 seconds. What is the mass of the particle? Now this is where, this is the type of problem where I generally just dump out a lot of equations and then just start piecing them together. It's like a quilt problem, as opposed to the 2-dimensional motion problem, which requires a kind of a set number of steps. First thing I need is rotation problem. Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. And we can get rid of those. The other equation that I need is 2 pi n is equal to theta. That the angle rotated is 2 pi times the number of rotations. I need to know that torque is the force times the lever arm, which is R. Oh, I do need an R. R is 3 meters. The last thing that I need is I need the rotational version of Newton's second law. Sum of the torques is equal to I alpha. There's one torque because there's one force, so Fr is equal to I total alpha. Now this can be simplified to this because stuff is 0. I'm going to substitute theta with 2 pi n. solve for alpha, and then take this and plug it in here. With problem solving, you're taking equations and plugging it into things that you do not know. If you spot it as an unknown, there's a good reason that, or there's a good chance that you can substitute in it, or substitute it out. This makes this F R I total alpha 4 pi n over t squared. Now what I'm going to do right now, it can get a little bit unwieldy if I'm rewriting this equation and I'm expanding the moment of inertia. So what I'm going to do is I'm going to get a value for that moment of inertia. T squared Fr over 4 pi n is equal to the moment of inertia total. That means it is 300 squared 400 3 divided by 4 pi 100. So 300 squared times 3 divided by pi. So I got 85,944 kilograms meters squared. That's the value of the total moment of inertia. Probably in a problem like this, I would say, give me the total moment of inertia and then give me the mass, the particle mass that we have out here. The total moment of inertia is the moment of inertia of the disk plus 3 times the moment of inertia of one of the particles. The moment of inertia of the disk is 1/2 mass of disk r squared. The moment of inertia of a particle is the mass of the particle r squared. What I'm looking for is MP. So I total minus 1/2 mass of disk r squared is equal to 3 mass particle r squared. Solving for MP, I have 1 over 3r squared IT minus 1/2 mdr squared is equal to the mass of the point. One over 3 squared, 85944 minus 1/2 mass of the disk, 100 3 squared, close, and that gives me $3,166 kilograms. So it's a big value, but I mean, I just did this problem on the fly. So it's just the general outline of steps. I could pick anything. I could make it a stick and then ask for the mass of the stick. I could ask for alpha. I could ask for the force causing the acceleration. I could do all sorts of things. But these equations here, also I would add 2 pi f is equal to omega. AR is v squared over r. V is omega r. Some of those other equations that could be useful, but in this case weren't used. Knowing these equations would help a lot. All right, it's 3:40. We only have 5 minutes, so there is really not time to do anything more. Tomorrow, 1 o'clock, right here We'll go over some more final stuff.